All right, back again. Now it's time to work on the next chapter, chapter 4. Chapter 4, um, section 4.2. Let me switch to a black pen. Is on Fourier series and the Fourier transform. But today we're just gonna review Fourier series, which is kind of a review from 2220. It's all based on, of course, Fourier's theory that we can take any periodic signal um, and write it as a sum, k equals minus infinity to infinity, of some Fourier coefficients, ck, e to the j omega naught t. So this is the complex um, Fourier continuous time Fourier series. Continuous time Fourier series. Okay, and we're going to focus on the complex version of this Fourier series, if you might remember from last time. Um, this is called the synthesis equation because we can take, if we know the CKs, we can synthesize the original signal. Maybe this is a cell phone and we transmitted the coefficients, and at the other end they can regenerate the original speech signal. The analysis equation allows us to find the CKs, the Fourier coefficients, we take the fundamental period, integrate over any range of t0, any full period, so there's the analysis equation. Okay, so we got analysis, synthesis, and we go back and forth with this thing. If we plot the CKs, we get various versions of the spectrum of the signal. For example, if we plot the magnitude, it gives us the magnitude spectrum. And if we plot the angle, it gives us the phase spectrum. And in the event that x of t, in the event that CKs are real, then we don't need two different spectra. We can plot them all if we want on a single graph. We can just plot the CKs themselves, and we get the amplitude spectrum. But in general, and CKs are complex, we usually plot the magnitude and phase. Hardly ever you ever see anybody plot the real part and the imaginary part, because it has very little physical meaning. So for example, here's an example plot. We get lines. We draw like red. So we get something like this and this. So there would be something that we'd get with when we plotted the magnitude spectrum. Okay, plotted against K. Now, quite often we actually want to plot the C's as a function of F. So when we do that, then this is 0, and this is F naught, the first harmonic, 2F naught, 3F naught, and then in that case, this is no longer K, it's actually frequency F in hertz. Okay, so that's the C coefficients as a function of f, and as we go along, we'll gradually just call that x of f. Okay, so so this is the magnitude. I should put magnitude bars there. This is C0, this is C1, C2, and C3, etc. All right, C0 is the DC component. And CK is the kth harmonic, corresponding to the kth harmonic frequency, KF naught hertz. Okay, so that's the kth harmonic, and that's the kth harmonic frequency. We also, as I say, if we want to draw the phase spectrum, we could, quite often we draw that right underneath, and it might look something like, maybe even draw some negative frequency terms. So we might have something that looks like that, that. So there's the angle of C1 right there. That's the angle of C2. C0 angle, I better draw that a little more legibly. The angle at the origin is generally taken to be 0. The angle of C0, 0. And there, of course, is the angle of C minus 1. It's a little more legible, etc. Okay. And again, we could write it on the same frequency axis. This is F0, 2F0, etc. And the phase spectrum is usually represented between minus pi to pi. And it doesn't so much matter where you put the less than or equal to signs there. All right, well, remember, this is for periodic signals. So when you have periodic signals, we always get what's called a line spectrum. Always get a line spectrum. And that means all of the energy, all of the power in the signal is concentrated at these discrete frequencies. There is zero energy in between these frequencies. All right, it's all concentrated at the line. So if we put this on a spectrum analyzer, we actually see these lines popping up with no energy between them. So that's what's called line spectrum. And if ever we see lines on a spectrum analyzer, we know that we've got a periodic signal component. Symmetry conditions. We won't prove this. It's kind of review from 2220, but you might remember that assuming the original signal is real, then we get these symmetry conditions that we can rely on, and they're very useful. The first one says that if we take CK and then we look at the minus frequency version, we look over to this side, they're complex conjugates of each other. So that's commonly called, surprisingly enough, conjugate symmetry. It has two consequences that are actually a little more useful to us. The first one is that the magnitudes between minus and plus frequencies are equal. This is even symmetry. So it means that if you look at the magnitude spectrum, you might get something that looks like this on one side, and it's just going to be the mirror image on the other side. Okay, so that's even symmetry for the magnitudes. And for the phases, we're going to see that there's odd symmetry. And I've kind of drawn it up here. There's a case where there's odd symmetry. So I'll draw it down here again. So if you see a phase spectrum, it's generally going to look, it's going to have this odd symmetry. My bad. Start all over with that one. It's going to have odd symmetry about the origin. So if there's something that looks like that on one side, again, it always goes through the origin here because that's what you need for odd symmetry. It's going to be the flipped mirror image for the other half of the axis. So minus frequencies, you flip it left to right, and you flip it top to bottom, and you get this odd symmetry.